Okay, so we'll talk about, this is like an introduction to queuing theory. Queuing theory is a branch of mathematics that falls under a topic of mathematics called operations research, which is a popular branch of mathematics in the UK. A lot of UK schools have a department of operations research. A few schools here have it too. Princeton University has an operations research department. And queuing theory is part of operations research. So what we'll go over is just kind of an introduction to some of the notation and just the idea of, what queuing is. Okay, so for example, if we have a queue, we have, this could be like if you went to a supermarket and you get online to check out your groceries, and then you get up to the cashier, and you pay the cashier and you leave. So when you show up at the queue, you get in line, and the server is serving, the next customer, and then the next customer, eventually they get to you, and you get served. So we want to look at how long it would take you when arriving to one of these queues. How long would it take you to get through the queue? So a couple of things we want to look at. It's very popular to use the Greek letter lambda to mean the rate at which customers are arriving to the queue. So customers could be showing up, like at a supermarket, what's a common rate for a customer showing up online? What would you say? 2 per minute, or? Yeah, 2 or?
Yeah, 2 per minute.
Maybe about 2 per minute. And then how fast can the cashier serve a customer?
45 seconds.
Well, that would be a problem, right?
30 seconds.
Right, so if they did 30, if customers were showing up at a rate of 2 per minute, which is the same as once every 30 seconds on average, the cashier would have to be able to serve at least 2 per minute. Otherwise, the line would grow.
So like 20 seconds.
Okay, yeah, so something like that would be okay. That would mean the cashier would have some idle time. Okay, so we'll use the Greek letter lambda to mean the rate at which customers are arriving. And we'll use the Greek letter mu to mean the service rate, or the rate at which customers can get served. Capital T will be the mean service time for each arrival, how long it takes from when you enter till you get served. So now there's the idea of what percentage of the time is the server, or like the cashier in a supermarket, what percentage of the time are they in use? Are they serving somebody? And what percentage of the time are they idle? So we're going to use the Greek letter rho to represent the utilization of the server, or the percentage of time the server is in use. Capital Q will be the number of customers in the system waiting or being served. So that would be someone who's either in service or waiting in the queue at any point in time. And we can have the number of servers, so you could have many cashiers at a supermarket, or we could have one. And the response time is going to be how long it took from the moment you entered the system until the moment you left the system. Okay. So when we're talking about the service rate, the service rate and the service time are reciprocal of each other. So if the service rate, so what'd you say for the cashier? So the cashier could be 20 seconds per customer, which is a rate of 3 customers per minute, right? So 20/60 is 1/3 or 3 customers per minute. So we're really saying the same thing. There's 2 different ways to say the same thing. So for example, a cashier can serve 1 customer every 3 minutes. Well, this would be like maybe like a Target or something like that, where people are buying a lot of stuff. So we could say the service time is 3 minutes. It takes 3 minutes to service a customer. We could say that another way. We could say the service rate is 1 customer every 3 minutes, or put another way, 1/3 of a customer per minute. Really saying the same thing, 3 different ways. And it's popular to use X, sometimes X with a dot over it, sometimes X with a bar over it, to mean service time. So the service time is 3 minutes. And the rate, mu, is 1/3 per minute, 1/3 of a customer per minute. So just, remember, a rate is an amount divided by a time, and service time is an amount of time divided by the amount of time per service. So it's two ways of saying the same thing. Sometimes the queuing questions will give mu, and sometimes they'll give x or x bar. Okay. So an interesting observation is sometimes called Little's law or Little's result. If you like to Google things, you type in Little's law or Little's result. And just using this notation again, lambda is the arrival rate. W is the mean time of process spent in a queue. N sub q is the number of processes in the queue. You can let WS be the mean time of process spends in the entire system, queue and service combined, and the number in the whole system could be the number of processes in the entire system. So Little's result is basically this equation. The number in the system is equal to the rate into the system times the amount of time spent in that system. That's true for the system, and it's also true for the queue part of the system. So for example, hopefully this result is intuitive. So for example, if 10 people walk into a supermarket every minute, and on average they stay for 30 minutes, so that's shopping and cashing out and all of that. How many customers are in the supermarket at a random point in time? The answer would be N, the number of customers in the supermarket would be the rate into the supermarket, 10 per minute, times the amount of time they spend, which is 30 minutes. So on average, there would be 300 customers in the supermarket. So I guess that would be a big supermarket, right? Maybe it's like in Manhattan, that has this many people coming in. Okay, and then one interesting question, I won't answer it here, but are there always exactly 300 people in the supermarket? If let's say the manager observed over the course of a day, they're coming in at 10 per minute, 10 every minute, and they also notice on average they stay 30 minutes. Maybe some stay 40 minutes, some stay 20 minutes, but on average they take 30 minutes. Could you make the statement there's always 300 people in the supermarket? Well, that's just a running average.
Yeah, it's just an average.
Okay. If actually they were showing up at exactly 10 per minute, like at the beginning of the minute, they showed up exactly 10 minutes, and they all stayed for exactly 30 minutes, then we could say there's exactly 300 in the supermarket at a time. But it's good to know that, because we're going to get into this discussion, that the average time between them could cause the number in the system to change. The averages will stay the same, but they can still change. So let's talk about the inter-arrival, the time between arrivals. And let's look at one extreme. One extreme is when the gap of time between each arrival is exactly scheduled, perfectly scheduled to be the same. So suppose you had a bus company that sends a bus to a bus stop once every hour. And let's say it's a very well-run bus company. And the bus always shows up on time. It's never early, it's never late. A bus shows up at 1 o'clock at the stop, then a bus shows up at 2 o'clock, and then 3 o'clock, and so on. So we would call the distribution, the probability distribution from between each arrival, we would call it deterministic. It's a deterministic probability distribution, means we know exactly when they're coming. So not only do they have the rate of 1 per hour, we know exactly when they're coming. So for example, if the last bus left the stop 20 minutes ago, can you tell me when the next bus is coming? How much time from now? If the bus comes every hour, and now I just tell you, and I tell you the last bus just left 20 minutes ago, can you tell me when the next bus is coming?
Yeah.
40 minutes from now, right? Because they're scheduled exactly. And this is going to show up in our queuing. Suppose someone is, well, let's say that we had a deterministic service. If someone already had 20 minutes of service done, and they take exactly 1 hour of service, we know they have 40 more minutes to go. Okay, so so if the last bus arrived 20 minutes ago, when is the next bus? It's going to be 40 minutes from now. If you arrived at the bus stop, let's say you didn't know the bus schedule, so you just showed up at the bus stop at some random time. On average, how long would you expect until the next bus comes? Yeah, 30 minutes, okay, right. So it's going to be somewhere between 0 and 60 minutes, all uniformly distributed, so you would probably show up at random in the middle, which means on average you'd have 30 minutes to go. Okay, so what we're saying is not only do we have a rate, 1 per hour, we also have additional information. We know that the arrivals are perfectly scheduled. And going back to the question we just had before, can we say that there's always exactly 300 people in the supermarket? The answer is no, unless the arrivals are all perfectly scheduled and the departures happen at exactly every 30 minutes, then there will be exactly 300 people. But if the distributions between the arrivals and the service are somewhat random, then we may sometimes have more than 300 and sometimes less than 300, with an average of 300. Okay. Okay, so now if we were to look at the service distributions, so let's say, for example, we're looking at the inter-arrival distributions, but we're now going to look at the other extreme, the opposite of being perfectly scheduled. We're going to say totally randomness between each arrival, complete randomness between them. So it's popular to call it's actually called the exponential distribution, and a famous French mathematician named Poisson did a lot of research in the exponential distribution, so sometimes it's referred to as the Poisson distribution. And that's one of the many types of another famous mathematician, Russian mathematician, Markov, talked about Markov processes, and a Poisson process is a subset of Markov processes. So it's also popular to call these Markovian distributions. But the idea is that an event happens with a rate, but the gap of time between each event is totally unconnected to the last event. So one example might be if you guys play roulette in a casino. A roulette wheel has 38 numbers on them, 0, 00, and then the numbers 1 to 36. So if you have a favorite number, like let's say 15, if there's nothing wrong with the wheel, the number 15 will come up 1 out of every 38 spins. That will be the rate. The rate will be 1 out of 38 spins. Your number 15 will arrive 1 out of 38 times. So now the question is, if the last number 15 arrived 20 spins ago, then when will the next 15, when would you expect the next 15 to have? 18 spins. Now that would be the correct answer if the wheel guaranteed that every 38th spin was the number 15. Then if it was 20 spins ago and it comes up once every 38 spins, then we know it will be 18 spins from now.
So it's the way of 1 in 38 chance.
Right, every time you spin the wheel, there's a 1 out of 38 chance it'll come up, which means, if there's nothing wrong with the wheel, it'll come up 1 out of every 38 times. But then the question is, if I tell you information about the past, if I say, well, the last time it came up was 20 spins ago, when will the next one be? Does the fact that the last one came up 20 spins ago even factor into when the next one will be? So like, for example, if I told you it hasn't come up for 37 spins, would you say it's definitely coming up on the next spin? Or what if it came up 3 times in a row? Is it now going to definitely come up a 4th time in a row, or it's not going to come up for 38
So
spins?
the path doesn't matter.
Right, so this is the case. So Poisson distributions and all Markovian processes, the past gives you no information about the future. Whereas in the pretty much any other distribution, the past helps you somehow. So this is the one extreme we talked about last slide was when it was perfectly deterministic, we know exactly when everything's going to happen. This is the other extreme. This is we have no idea when the next one is coming. Even if we know everything about the past, we know nothing about the future. We just know the average. It comes up once every 38 spins. So let's see, if you arrived at the roulette wheel at an arbitrary point in time, how many spins would it take until the next 15 shows up? Well, that's actually the same question. These two questions are actually the same. If it's been 20 spins since the last one and you show up, how long would you expect to wait till the next one? And if you showed up at a random time, when would the next one be? The answers would actually be the same. Past information doesn't have any, doesn't help us.
So
Oh.
what would it, just, you don't know?
What would the answer be?
Yeah.
Okay, so now if we wanted to know how many spins would it take, and maybe you've had a question like this in a probability class, maybe the simpler version might be, how many times would you have to flip a coin until the first heads came up? I don't know if that's come up, and you guys know that's 2. Right, so there's a 50% chance it'll be on the first flip, 25% chance it'll be on the second flip, 1/8 chance it'll be on the third flip, 1/16 it'll be on the fourth flip, but on average it averages out to 2 times the flip. And you would do a computation something like this. You say, okay, the expected number of spins of the roulette wheel before the first number 15 comes up would be the variable e. So that's the thing we're trying to solve. Well, we know we got to spin the wheel at least once. And 37 out of 38 times, we're not going to get the result we want, and we have to start over. We would have to start everything all over again. So this equation would be true. The expected number of spins, if you were to start right now, how many spins would it take until we get our first number 15? Would be 1 spin plus 37/38 of starting over again, whatever the expected number of spins from that point is. So we know this is a true equation, we just don't know what E is. So if we subtract 37/38 E from 38/38 E, we get 1/38 E is equal to 1. And then if we multiply both sides by 38, we say the number of the expected number of spins until our number comes up would be 38. So if you kept betting on the same number, you could expect to win 1 after 38 spins. And the casinos generally pay 36 to 1, so there's a little advantage to that in doing it. So if you play 38 times, you would get $36 back and lose $2 on average. But there are people who go to a casino, there'll be people standing there writing down the numbers with the past, and then they make their big bet, and the past means nothing in the future. If that actually worked, the casinos would go out of business. So, okay. So just to kind of draw this out in a picture, if the arrivals to a queue, so this is really time going this way. If the arrivals to a queue are perfectly scheduled, so these arrows hopefully are all spaced out exactly the same. Hopefully it looks like that. So a customer is being served. So let's say in this case, lambda, the arrivals are 2 per second. So I guess this would be 1 second, and then this would be 1 second, and this would be 1 second. So the arrivals are 2 per second, and the service rate, the server can serve at a speed of 3 per second, or it will take 1/3 of a second to get a customer served. So a customer arrives, and then they're being served, and right here their service is done. So now the server is sitting idle. So if this was like a cashier, the cashier's playing on Facebook until the next customer shows up. Then the next customer shows up a half a second after the first one and gets served for 1/3 of a second, and then is done. Next customer, so then the server is idle, then the customer shows up, goes right into service, doesn't have to go in the queue, gets served, gets done here. Server is idle, another customer shows up, gets served and leaves, and this keeps happening. So if we had a queue where the gap of time between each arrival was deterministic. That's what this first B is. So the letter, we'll get into this notation, Q's notation shortly. But if the arrivals are deterministically spaced with an arrival rate of 2 per second, and the service times are deterministic, they all take exactly the same amount of time with a rate of 3 per second, then every time a customer shows up, how many customers would that arriving customer expect to see in front of them? If the arrivals are all perfectly spaced, you know, the same exact distance between each, and the service times are exactly 1/3 of a second each, then when a customer arrives, like when this customer arrived, how many customers were in the queue before them? Yeah?
I have a question.
Yes.
You said the service times are 1/3 each, but the lines are covering up like about 2/3 of the space.
Well, the service time, the service speed, the rate is 3 per second, which is like 1/3 of a second each. So this is actually 1 second. Maybe I should have put.
Okay.
Right, because the arrivals are 2 per second, so that's 1 second, and then that's 1 second. So to arrive every second, each arrival takes exactly 1/3 of a second. Not only do they average 1/3 of a second, they take exactly
So
1/3.
if each arrival per second is 1/3 of a second, there's 2 arrivals per second.
Right, each arrival, the cashier takes, or the server, takes exactly 1/3 of a second every time. It's deterministic, so we know exactly how long it takes. So if that were the case, if the gap of time between arrivals was deterministic, and the amount of time the server spends was also deterministic, then any time an arrival shows up, what can it expect to see in front of it? Nothing. It's guaranteed there'd be nothing. Because the server can get rid of the previous arrival guaranteed before it arrives. Now let's look at the other extreme. So obviously this would be better because it's less congested when you arrive. The other extreme is where we're going to say that the arrivals are, the gaps between the arrivals, like a number coming out on a roulette wheel, they have an average rate, but the gaps between them are totally random. It would be like you were told on this period of time you get 4 arrivals and you just close your eyes and threw 4 darts and it can show up anyway. So what we might have is the first arrival comes, goes into service. While the first one is in service, the second one comes, but the first one is still being served, so the second one is queued up. Then the first one finishes at this point in time. Now the second one immediately goes into service and stays into service, and maybe this amount of time is much smaller than this amount of time because the amount of time in service are random with an average of 3 per second. So the third arrival comes while the second customer is still being served. Then the second one finishes, so the third one immediately goes into service, and it's a very short one, so it eventually finishes. Now the server is idle during this time. Then a fourth arrival comes, goes into service, and then ends at that point. So the amount of time, the percentage of time that the server is idle is still going to be the same as before. And the percentage of time, I'm going to use the letter rho to talk about the percentage of time the server is idle, is going to be the rate in divided by the rate out. If the rate in equaled the rate out, it would be 100% in use. And then as the rate in gets slower, the idle time builds up, and as the service time gets slower, the idle time will drop. So now, if an arrival was to come up, to show up at any time, on average, what would it expect to see in front of it? So this is a different case. This is the case where the distribution between arrivals is totally random, like a number coming up on a roulette. And the amount of time it takes to serve a customer is on average 3 per second, but again, totally random. Here's a moderate sized one, here's a long service time, here's a really short one, and then here's a moderate one. But they average 1/3 of a second each. So an arriving customer in this case, could they expect to see I wouldn't say expect, but is it possible they could see customers in front of them? In this case, it would be. So if we wanted to calculate how long it takes to get through the queue, if we wanted to calculate how long it takes when you arrive at a cashier at a supermarket, you wanted to know how long would it take for you to get through the cashier, you'd have to look at all the customers who are in front of you, figure out on average how long will they take each to get through the cashier, and then how long will you take to get through the cashier, and that's how long it will take you to get through the cashier. So we just wanted to have a little discussion that not only are the arrivals coming at a rate, and the server can serve at a rate, but also the gaps of time between them is going to actually change our answer. It's going to change our answer for how much stuff is in front of us, how much stuff is in the queue. Okay, so just going over some of the notation. If you Google Kendall notation, someone named Kendall gets credit for how to label queues. We could use up to 6 letters. Capital A, capital B, small c, capital K, small m, and z. So the first letter, A, is the distribution between the arrivals. It could be deterministic, meaning perfectly spaced. It could be Markovian, meaning totally randomly spaced. Or it could be other distributions which might be hybrids of the two. There's many distributions we can use. The second letter is going to be the distribution of the service times, how much of a difference there is between service times. The server could have there could be one server, or there could be many servers, like when you go to there's a place where you have one line and then many servers, like a bank. They don't even go to banks anymore. But a place where everyone gets in one line and then it fans out to many servers. Well, we could have many servers if we want. Theoretically, like at a bank, the line just goes on forever, right? So if the line gets too long, they just add more of those rope things and the line just keeps going. But you could have a finite capacity queue, which means if the queue is full and you arrive, you immediately have to leave. You won't be served. So some queuing systems have a finite capacity, some don't. We could also have a closed system where you go through the queue, and when you get through the queue, maybe you go to another queue, and eventually you get routed back, and you always stay within the system. So customers aren't being added from the outside world, and nobody ever finishes and leaves. It's just a finite, enclosed queuing system where customers are bouncing around. And then the last thing we can put down is the queuing discipline, whether it's like first come, first serve, or shortest time goes to the front of the queue. There's different disciplines we can use. So for example, we could say something like we can have an A/B/c queue. This could be used. This is where we're using 3 of those 6 letters. We can say, we can use that, and that's probably the most common you'll see. If there's no limit on the length of the queue, so we don't have to have the 4th letter that says how big the queue is. The source, the customers are infinite, so it's an open system. Customers are coming in from the outside world, they participate in our queuing system and eventually leave our system. So we don't have a finite number of customers. And by default, first come, first serve is the default queuing system, queuing discipline. And as far as the A and the B goes, we can have the general independent interarrival times, general service time. Erlang has, a famous mathematician named Erlang has a series of distribution which are hybrids of the 2 extreme cases. M is used for an exponential, which is sometimes called a Poisson process, which is a form of Markovian process. A D can be used to mean deterministic, where everything is perfectly scheduled. And yes, and then there's many other distributions. And fortunately or unfortunately, when we analyze operating systems, we will look at devices like the CPU and the disk drive, and we'll say, when do customers arrive to these, and how long does each service take? And we may have to even come up with our own distributions for those. Okay. So a queuing system like this, here's an example of a closed system. This is where we have 12 processes. Maybe they go to some people here who are thinking, and then every once in a while they send in for some kind of service. And we have a queue that has exactly 4 seats in it. So it's a finite sized queue. You work your way through the queue, and then you can go to any one of these 3 servers. After you finish service, you go back to the beginning of our system. So there is no way to enter the system, and there's no way to leave the system. So the Kendall notation for this system, if let's say these people are thinking randomly, and then every once in a while they just need something done, maybe these are 3 printers or something, they need something printed, they send their request into the queue, and if the servers have a certain service time and every request takes the same exact time, this could be a Markovian, meaning totally random, spacing between arrivals to the queue, but a completely deterministic service time. They all take the same amount of service time. So this could be an MD3, meaning 3 servers, /4, meaning 4 seats in the queue, /12, meaning 12 customers in the closed system. And then this could be a first come, first served queue. We could actually could have left that out because we've decided that first come, first served is the default queue. So a picture like this could be an MD3, 4, 12, first come, first served queue. Okay, and then we could have a queuing network. We could have a queue, let's say queue jobs or processes arrive at this queue, they go through the queue, they get served, and then once they leave this, they leave maybe 30% of the time they go to this queue, and 70% of the time they go to this queue, and then when they're done, they go back to this queue, and they just keep going like this. So this would be a network of queues where the output of one queue feeds other queues. So the response time to a system like this, if it was an open system, would be the time from the time you came into the system until the time you left. The throughput is the amount of work divided by the amount of time it takes to get the work done. Out of all of these queues, since they are all networked together, we could calculate the value of rho, the percentage of time each of these servers are in use. And we could let the number of customers come into the system until what would be our limit on how many customers we can allow in the system. So suppose, for example, let's say, for example, this queue is for the CPU of our operating system. So suppose, for example, customers come here, they process, they run instructions, and maybe 30% of the time they hit a page fault, so they have to go out to the disk drive. And maybe other processes are in the disk drive, so they queue up and they get the page that they want. Is that a page fault? Page gets loaded into memory. They use some algorithm like least recently used to figure out which one to replace it on. And then they go back and they go back to the processor again. And maybe 70% of the time, they leave and maybe they do a P of X function. They ask for a resource that's not available, so they have to get put on a queue waiting for it. Then the resource eventually becomes available. Some other process does a V of X, and then they can start processing again. So you're just bouncing around from queues to queues. So suppose I told you that the CPU is being utilized 80% of the time, and the disk drive is being utilized 50% of the time, and the semaphore queues are being utilized 60% of the time. Could we add more customers to this system? Well, what utilization of a server would make us say we can't really add anything more because now the queue is going to... What gets us to 100% utilization? That would be if the rate into the queue equals the rate out of the queue. And if we added more customers, that queue is just going to grow off to infinity. So if any one of these queues if any one of these servers hits 100% utilization, we can't add any more customers. So the device, the bottleneck device, or bottleneck devices, are out of all of our queues, which one has the highest utilization? And we know we've hit a saturated system when we have at least one queue at 100%. One of the servers is at least 100%. We have a saturated system. We can't add any more customers because the queue that's at 100% is now just going to grow off to infinity, and then no one will get through the system. Okay, so a very common, probably the most popular queue analyzed is the MM1 queue. That's where arrivals come into the system. They first come, first served. The system is open, so you come in from the outside world and you leave to the outside world. And there's only one server. And the amount of time you spend in the service, the distribution of the amount of time is completely random. So it's an MM1 queue. So suppose we had an arrival rate of 1 per second and a service rate of 1 per second. What would the utilization be in this case? What percentage of the time would the server be in use? So if customers are showing up 1 per second on average, the gap of time between them is totally random, but the average is 1 per second. And the server takes, on average, 1 second per customer. What percentage of the time will the server be in use? 100%. 100%, right. And actually, yeah, so now, theoretically, this is, I guess, I'm just asking some intuition here. If this was a DD1 queue, what would actually happen is every time a customer arrived, which would arrive 1 every second, they'd go into service. The second they the instant, not the second, the instant they finish, the next arrival would come. So nobody would be in the queue. The server would be in use 100% of the time, but nobody would ever get to the queue if it was a DD1 queue. But if it's an MM1 queue, what would your intuition be on how many would be in the system? Because you would think the server can handle the crowd. You know, they would be busy all the time. They can handle the crowd. So intuition might, so a couple of interesting questions might be, you know, what percentage of the time is the server in use? This one would be 100%. What would be the mean time you'd spend in the system? We'd have to know how many on average are in the queue, and then we get put in the queue and how long does it take us to get through? And what would be the mean time in the queue? To know the mean time in the system, we'd have to know the mean time in the queue. So intuition might lead us to think, yeah, the server would be 100% in use. But when we go through some of the analysis of what is in this queue, which we'll talk about next class, the size of the queue is actually going to, does anyone have an instinct? What,
I just had a question.
Yeah.
But how do we know it would be 100% in use? Because like say if someone showed up right away, the next person won't show up until 2 seconds.
Yeah, that's actually a good,
You know what I'm saying?
a good point. So what you're saying is at the beginning of the day,
Yeah.
in the beginning, a customer shows up, gets served very quickly, and now the server's waiting a little bit for a customer to show up. Yeah, at the very beginning, there'll be some times when the server's idle. But as the day goes on, then it would get to the point where the total arrivals is equal to total service time, then it would get to 100%. So when it hits the steady state, not at the very beginning. But that's a good observation, that initially the server might have a couple of moments when it's first turned on, that it's idle. But then it'll go to 100%. Yeah, what's kind of interesting is the queue will theoretically go off to infinity. I would think it would just hit some kind of average size and still there wouldn't be congestion. It's too bad, but okay. And then let's see. Okay, and then just a couple of things as maybe if we start networking queues together. If a queue had 2 sources of input, let's say we had a queue over here and a queue over here. We have 2 sources of input. One source is sending customers in at a rate of 2 per second, and another source is sending them in at a rate of 1 per second. Then what's the input rate of the entire queue?
3%.
Yeah, we just add them together. Assuming these customers are of the same type. Now, we can make the problems get real interesting when we have two types of inputs. Slow customers and fast customers, you know. Customers who have 6 items or less, and then customers have a whole shopping wagon full of items. So then you go in through the queue, and then what if we had 3 servers that had, that serve at a rate of 4 customers per second? So this one could do 4 customers per second, this could do 4 customers per second, this could do 4 customers per second. And we have 3 of them. So now for a queue like this, what is the input rate and what is the output rate? So the input rate, lambda, is lambda 1. I probably should have called this lambda 1 and lambda 2. Lambda 1 plus lambda 2, which is 2 per second plus 1 per second, so it's really 3 per second. 3 customers are showing up to the system per second. The individual mu's are 4 per second, but we have 3 of them. So when all 3 customers are being used, the server system can serve 12 customers per second, right? 3 times 4. So the percentage of time that the typical server is in use would be, it's always lambda over mu, but now in this case it would be lambda over, we use the little letter c for the number of servers. Lambda over c mu, which would be 3 over 3 times 4, which is 25% of the time. So these servers will be in use, each one individually will be in use 25% of the time. So another way we can get questions, you know, if you took up like a full semester course in queuing theory, you could have a discipline that says of these 3 servers, when they're all idle, the next customer always goes to this one. Then if this one is in use, the next customer goes here. If these 2 are in use, the next one goes here. Then the statement, each one of these on average is free 25% of the time is not true, because this one is in use more than this one, and this one is in use more than this one. But if they were coming out of the queue totally randomly going to an available server, then each one would be busy 25% of the time, and therefore they'd be idle 75% of the time. So you can kind of see, you can take these examples and just make them bigger and bigger and bigger by having new rules. And you could have rules on the queuing discipline instead of being first come, first serve, meaning you come into the end of the queue and work your way through. It could be a priority queue. Maybe you come into the middle of the queue. And so you don't care about all the customers who are in the queue, you just care about all the ones who are higher priority than you. They'll be in front of you. But now you also have to take into account, when you come in, while you're waiting in the queue, someone of higher priority may show up and jump in front of you. So you have to take that into account. So a lot of twists you can do with these questions. So this is just, like I say, a good introduction. Any questions just about the introductory topics?